Good day. This video will discuss the STPM Past Year in 2020, Section A. Let's begin. Electric field strength at a distance of 0.5 meter from a point charge is at 0.9 times 10 to the power 3 Newton per coulomb. And the field is in the direction towards the charge. So this should be the negative charge. What is the value of the point charge? So this is the formula of electric field strength. Just key in the value and you should be able to obtain the answer. So what we have is the electric field strength at 0.9 times 10 to the power 3 multiply 4 pi epsilon r squared. So r is 0.5 meter squared. So answer would be 2.47 or 2.5 times 10 to the power negative 7 coulomb. And it is a negative charge. Answer is C. Proceed to question number 2. Two parallel plates X and Y have opposite charges and separated at a fixed distance shown in the diagram. So which graph shows the variation of the magnitude of electric field strength with distance r from x? So we learned about this, that the electric field strength should be constant regardless of distance. So answer will be A for this test, and we move on to question number 3. Capacitance of a parallel plate capacitor is, so this is the formula, and let's study all the answer. Independent of dielectric is wrong, inversely proportional to the area, also wrong. Directly proportional to the distance between the plates, also wrong. Independent of the potential difference across the plates of the capacitor is correct. So potential difference only affects the total charge that can be stored in the capacitor. So proceed to question number 4. A parallel plate capacitor is constantly charged by a battery. After several minutes of charging, a slab of dielectric material with dielectric constant epsilon r is inserted in the space between the plates of the capacitor. The battery remains connected, so it means that the potential difference across the capacitor is still constant. What is the ratio of the energy stored before the slab is inserted to the energy stored after the slab is inserted? So I want to compare the energy before and after. So we have formulas E is equal to half CV squared and also half Q squared over C. So you should identify what is the constant variable in this case, that it is the potential difference. So we should use the formula of half CV squared. And we can see that the energy is proportional to the capacitance. So energy stored after the slab is inserted should be higher with the ratio of epsilon r. So answer will be equal to A, okay, 1 to epsilon r. And then we proceed to question number 5. When a steady current, so it's a constant current, flows in a non-uniform wire. So non-uniform means the area of the wire, cross-sectional area of the wire is not constant. So the current density is, okay, so what is it? So we know that current density is I over A and is equal to NVE. And since it's a non-uniform wire, so we have a non-uniform current density. Constant along the wire is incorrect, directly proportional to the radius. So current density is inversely proportional to the area, so it should be inversely proportional to the radius. Directly proportional to the drift velocity is correct. Okay, we have J equal to NBE. So answer should be C. Inversely proportional to the density of free electron is wrong. Okay, it is directly proportional. So answer is C for this question. We proceed to question 6. A wire of resistance 21 ohm is melted and reshaped into a new wire of 3 times the length of the original wire. So if the volume of the new wire is equal to the original wire, what is the resistance of the new wire? So the question mentioned that the volume is constant and the wire is 3 times longer. So we have the formula of resistance is equal to rho L over A. And probably we need to re-express the resistance in terms of the volume as the constant variable. So we know that the volume is equal to the area multiplied the length of the wire. So here we could express as rho L squared over the volume. So here we can see that the resistance is indirectly proportional to the square of the length of the wire. So with this, we have 3 times the length. So the new resistance should be 3 squared, which is 9 times of the original resistance, which is 21 multiply 9. It should be 189 ohm. So answer will be A for this case. We move on to question 7. An electric circuit is set up as shown in the diagram below, which is not true about I1, I2, I3 when S is open. So when S is open, this is an open circuit that the current only flow through the outer path. So what we can do is we can expect that the I3 will be equal to 0. So answer A is correct. And then maybe you want to also, okay, so answer C is also correct because I1 and I2 is the same because they are now in a series circuit. So next is we're going to need to check which of the answer B or D is correct by applying the Kirchhoff law. So we can apply Kirchhoff law here. So for example, you would apply in a clockwise direction. So what we have is we have the 12 minus 9, okay, because the 9 is against the loop. So equal to the current multiply the total resistance in the circuit, which is 6 plus 9 ohm. So answer here will be equal to 3 divided by 15. 3 divided by 15 ohm. So the current in the circuit should be 0.2 ampere. So which is not true. So the answer would be D. Okay, I2 is not equal to 1.4 ampere. Okay, because I1 and I2 are equal, so it should be also 0.2. Proceed to question number 8. A circuit of a battery connects to a resistor is shown in the diagram below. What is the terminal potential difference of the battery? So terminal means that you need to include the whole things, which is internal resistance is also included. So to get the potential difference, what we can do is just apply the potential divider because the terminal potential difference of the battery is also equal to the potential difference across the 8 ohm resistor. So just apply the potential divider that we have 8 over total resistance is 8 plus 1, 9. Multiply the EMF of the battery, 4.5. So the answer will be equal to 4 volt. Okay, the answer is C. Now we proceed to question number 9. Potentiometer, a device used to determine the EMF of a cell Q, has a balance length L. Which procedure will give us a new balance length that is longer than L? So before we answer this question, maybe we can build equations based on the circuit first. First of all, that the wire has a linear relationship, where the length of the wire is proportional to the resistance, which is also proportional to the voltage applied. So this gives us the relationship of the ratio of the balance length to the total length of the wire is equal to the ratio of the potential difference across the balance length, which is the Q for this case, to the voltage across the whole wire. And then we also can determine the equations of the voltage across the wire by using the potential divider formula. So from here, now we can review each of the answer. So first of all, a resistor is connected across Q. So you should have learned that when you have a balanced length, there is no current flow through from the driver circuit to the current below. So A doesn't help anything. B, R is replaced with a resistor which has higher resistance. So if we have higher R, so this gives us a lower voltage of the wire. And if we have lower voltage of the wire, so this gives us a longer balance length. So answer would be B in this question. So next, terminal connection of P is reversed. So this also doesn't help because it will form a complete circuit from the driver to the circuit below. Next, Q is replaced with a cell which has smaller EMF. So we can see that balance length is proportional to the EMF Q. So this also doesn't increase the balance length. So the final answer should be B. And let's proceed to question 10. In Thomson's experiment to determine the ratio of the electron charge to the mass for electrons, the electron is launched with the velocity into a region consisting of cross-magnetic and electric fields. So this region is referred to the velocity selector. If the magnetic flux density is B and the electric field strength is E, which is true about the magnitude and the direction of the velocity of the electron. So it should be clear that the direction of the motion is perpendicular to the magnetic field and the electric field. So the answer is either C or D. And then we also learned that in the velocity selector, if the electron able to move in a straight line, it means that the magnetic force equal to QEB is equal to the electrostatic force QE. And from here, we can obtain the expression of the velocity, which is the ratio of the electric field strength to the magnetic flux density. So the answer is D. Now we proceed to the next question. The current flows in a conductor placed in the magnetic field of magnetic flux density B. The whole voltage is produced across the sides of the conductor, which diagram shows the correct direction of B. So the whole voltage is produced at the sides of the conductor. So the direction of the magnetic flux should be in a vertical position. So it's either A or B. And then for a conductor, the major charge carrier should be electron. So the current is flowing from the left to the right. So the electron will be flowing to the left. So now what you do is to apply the Fleming left-hand rule to check which of the answer is the correct one. And also please always remind yourself, this is an electron. So in the end, you should reverse the direction of your thumbs. And when you perform your Fleming left-hand rule, the answer should be B. In this case, that there will be a magnetic force push the electron in the upper direction when the magnetic field is pointing downward. Now we proceed to question 12. So a solenoid is wound with 5,000 turns on a hollow cardboard of radius 7.5 millimeter. If the length is 0.6 meter and the current flows is 3 ampere, what is the magnetic flux through the solenoid? So we learned about the magnetic flux is NBA, and the magnetic flux density inside the solenoid is given as mu naught Ni. So you need to memorize the formula. So we have all the information here, so you just key in into the formula and you should get the answer. So the magnetic flux is equal to NBA, where the number of turns is 5,000. Multiply the area first. So we have a radius of 7.5 millimeter, and we can use the formula of pi r squared. So pi times 7.5 millimeter squared. And then we're going to multiply the magnetic flux density that is given as mu naught Ni. So multiply mu, multiply n, where we have 5,000 turns over 0.6 meter. So 5,000 divided by 0.6 meter. And then we multiply the current 3 ampere. So the final answer is 2.8 times 10 to the power negative 2 Weber. Answer is C. Now we proceed to question 13. A short coil of 600 turns is wound over a middle part of a long solenoid of 2,000 turns as shown in the diagram. So if the area is 6 times 10 to the negative 4 meter square and the length is 0.75 meter, what is the mutual inductance between the solenoid and the coil? So if you can remember the formula of the mutual inductance, that is good. But for me, I prefer to do the derivations. So remember that flux is equal to Mi and it is also equal to NBA. And again, we will apply the formula of the magnetic flux density inside the solenoid as mu naught Ni. So the final expression of the mutual inductance is mu naught N1, N2 area divided by the length. So all the information are given, so just key in and we can solve this question. So we have the mu multiply N1, N2, 600 and 2,000 turns. Multiply the area, so it's given here 6 times 10 to the power negative 4 divided by the length 0.75 meter. So final answer is 1.2 millihenry. Answer is B. Question 14. A pure inductor L is connected to an alternating current as shown in the diagram. So this is a pure inductor circuit. So which graph represents the variation of the current and the power with time in the circuit? So for answer A, B, C, and D, so we can see that all the current are sine wave, and you should be clear that the voltage across the inductor is leading the current. So if I is a sine wave, so the voltage should be a cosine wave. So let's draw a cosine wave, and based on the waveform of the voltage, we can deduce the power. So the general formula of the power is equal to the product of the voltage and the current. So you can also do the derivations of the power, okay, derive the formula of the power, or we can observe the graph and we can do the analysis. So power is equal to VI. So we can check answer D. So you can see that in the first section, so both voltage and the current has positive value. So the power is positive. And then for the next section, so we can see that I is positive and voltage is negative. So power is in negative value. And remember that the power across the inductor or the capacitor has a double frequency as the voltage and the current. So the answer is D if you can remember the graph. Now we proceed to the last question, question 15. A resistor and a capacitor are connected in series to an AC current. So if the frequency is 60 Hz and the mean voltage is 45 volt, and what is the root mean square voltage across the capacitor? So the simplest formula is voltage across the resistor is IR, and the voltage across the capacitor is I multiplied the reactance. So if you divide, okay, if you do simultaneous of these two equations, then the current across these two components is equal. So we have the voltage across capacitor equal to the ratio of the reactance to the resistance. multiply the voltage across the resistor. So from here, we are going to determine the reactance of the capacitor, which we have the frequency as 60 Hz. So what we have is 1 divided by 2 pi f divided by the capacitance, which is 58 nano. So this is the reactance divided by the resistance, which is 20 kilo ohm. Multiply the voltage across the resistor, which is 45 watt. And the final answer is 103 watt. So this is how we can solve the AC circuit with the simplest formula. So that's all for the discussion of the STPM 2020 section A. If you still have any questions, you can leave it in the comment section, or you can join in the Telegram group to post your question inside the group. So that's all for today, and thank you for watching.